So like I said, no daily check. We're, right kind of in the middle of 2-4. I wanted to get through the long chain solving today before doing daily check on anything. So before we head into the next little theorem and rule, and this is another one that they love putting on the ACT. I hate that I will legitimately go on rants outside of the classroom about teaching to the test and how dumb it is, and here I am telling you, this is going to be on the ACT. Well, if you got to play the game, play it well, right? So before we do this, how about the homie work? Were we feeling okay about that? Those of you that actually did it? Any questions? Even my usual 2 or 3 didn't ask, so I assume that things went okay. All right. Congrats on everyone making it in on time, even with it getting sloppy out there. I have a very different definition of on time than some teachers. So, rational root theorem. Talked about that. Was all the factors of constant over all the factors of leading coefficient. Those are the possibilities. Along comes other famous dead math dude and says, there's a bunch of proof for it. In this case, I'm just going to say it's magic, believe it. There is a proof, and it's nice and simple. You saw it in Algebra 2. It says, I can count the sign changes in a polynomial, and it tells me how many positive and negative real zeros I got. Now, before doing that part, no, we can start with that, yeah. So there's 2 parts to it. First, I'm putting in a positive x. What happens to all of these if I replace x with specifically positive x? It's the exact same thing, right? 3 positives here and a negative. 2 positives here and a positive here with a negative. It's the same thing, right? So first up is positives. If I do g of a positive x, I'm not going to write out all of that stuff. Instead, I'm just going to write my signs so that I can count how many times it changes. It starts with a negative, then a positive, then a negative, then a negative. I count how many times did the sign change, because if the sign changes, think about what is in between negatives and positives. 0. In between negatives and positives is 0. So this is what, there's a proof for it, but this is what helps me determine the number of possible zeros, because it changed signs that many times. It went from negative to positive. There must have been a 0 between. So, green. It changed once, it changed twice, it stayed the same here. So, I would say there are 2 possible, because I put in positive x, positive real zeros. Yes, I left that blank space for a reason. There's going to be a little more there, if you remember from Algebra 2. If I instead put in a negative x. Well, I got triple negative here, and then negative 3. What is that? Positive. I got double negative here, and then positive. Double negative, and then positive is positive, right? It depends, okay? We'll look at which ones. I put a negative in here with a negative. And then this is a constant term, so I can't put in a negative x. It just is a negative 1. which ones change signs? But which ones specifically? X to the third and x to the first. Odds, right? If I got an even number of negatives, it's always positive. If I got an odd number of negatives, it's always negative. So think of negative as opposite. Odd ones will go opposite the sign. Odd terms or odd exponent terms are going to switch your signs. So it's a shortcut you can use instead of actually plugging in a negative x, or you can just plug in negative x, call it good. The sign changes. I only see one. Went from positive to negative one time. So I'd say there's one possible negative real zero. Now this is not 100% complete because there's a little something about these polynomials. Remember, how many total possible real zeros could a cubic have? So I'll just draw a generic cubic with 3 zeros. Right now, that cubic has how many negative real zeros? 1. How many positive real zeros? What if I move the cubic to right there? Same, right? Because this one happened twice. So it still has 2 positive real zeros, it's just it repeated. But if I move just a hair above that, how many positive real zeros does it have now? 0. Do you remember from Algebra 2 that these had to go down in pairs? Because if it's not a real zero, what kind of zero is it? Imaginary. What is imaginary? I. I is what? Square root of negative 1. How did we get that square root? We put it there. And if we put it there, the only way to get an imaginary root is to have a conjugate pair of imaginary roots. They always come in pairs. They're like Sith, always the master and the apprentice. Okay, there has to be 2 of them. So whenever I do this possible real zero thing, I always need to take my answer down in pairs because that possibility could have kept coming down in pairs. Show you for something bigger than a cubic, what if I took a quartic? Better yet, well, like that. How many positive real zeros does it have? 3. 1, 2, 3. How many positive real zeros does it have? How many positive real zeros does it have? 1. From 3 to 1. It goes down in pairs because those 2 real zeros became imaginary, and imaginary zeros always occur in pairs. Okay, what if the... Oh, you didn't do that for me, huh? Screw you, Frank. Fine. How many positive real zeros are there? 4. How many positive real zeros are there? How many positive real zeros are there? 2. How many positive real zeros? How many positive real zeros? 4 or 2 or 0. Always down in pairs because imaginary zeros happen in pairs. So this works no matter what your answer was up here. Say I had a big honkin' long polynomial and I saw 7 sign changes. I wouldn't just say there's 7 possible positive or negative real zeros. I would say 7 or 5 or 3 or 1. I don't go to 0 because that's not down a pair of zeros. Okay? So whatever I get from this sign change business, I have to remember to always go down in pairs. And how could this help me? Assume that you don't have a graphing calculator in front of you. How could this help you find your zeros? You did your rational root theorem. You've got 16 different numbers to try by synthetic division. How can this help you? See how the positive is 2 or 0? There might have been no positive real zeros at all. But look at the negative. 1. I know there's one negative real zero. So I'm going to start guessing and checking with my negative numbers. I'm not going to start guessing and checking with my positive numbers because there's a possibility that I do all 8 of those positive numbers and none of them work. I'm going to start with my negatives. Okay? This is, like, you ever do logic puzzles? Like elementary or middle school? You have to find out which person has which job, and it's got the, like, all the boxes, and it's like a table of, Sally, Timmy, Bobby, Steve are a plumber, a baker, a whatever, and you have to cross out options as they tell you things. That's what we're doing here. It's a logic puzzle in which you're eliminating options. So that's why they love giving you these in standardized testing, is because in the ancient days, this is how you had to do it. Well, thankfully for the last 30 years, we've had a graphing calculator. Okay? But this is called Descartes' law of signs. So I do want you to do both just to get a little practice with it. Anyone who's recently taken that ACT could probably confirm there is something like this on there. They love putting Descartes on the ACT.
Yeah, but I just used the calculator.
Another reason is I know we're kind of a mix of grade levels in here. If juniors do well enough on the smarter balance, they let the entire class just not show up for Spartan time as seniors. And the smarter balance test, they only give you a calculator under certain conditions. You don't get to bring in a calculator. If they allow you one, it's a pop-up on the program.
Oh, yeah, that's the junior state test.
Uh-huh.
I hated that. So long. True.
So, again, this is helpful. We aren't going to use it very often, but it is still one of those standards that I have to assess. So you plug in a positive, count your sign changes. Plug in a negative, count your sign changes. Should be relatively quick. So first up, if I put in a positive x, I'm just going to get the same thing. So I count the sign changes in the current polynomial. H of x goes positive, positive, negative, negative. F of x goes negative, positive, positive, negative, positive. You count the sign changes on them. H of x only changed once. F of x changed once, twice, thrice. So for h of x, I'm going to say it has 1. I can't go down in a pair from there. Possible, positive, real 0. Notice it says real 0, not rational. It's just a real 0. It might be cube root of something and, big nasty decimal. But it's real. It's there. I can see it. For f of x, since it went 1, 2, 3 sign changes, that tells me that there's 3 or 1 down in pairs. Yep. Possible, positive, real 0s. So before even going to the negatives, this tells me I should guess and check positive numbers for both of these, because both of them are going to have at least one positive real 0. Negatives. If I put a negative x into an odd, it changes signs. A negative x into an even, it keeps its sign. A negative x into an odd, it changes signs. That's a constant. It is what it is. A negative x into an even keeps its sign. Negative x into an odd changes its sign. Negative x into an even keeps its sign. Negative x into an odd changes its sign. Constant is just constant. And if you need to write it out, remember, every time you hit a negative, negative means opposite. You ever seen those old arcade games where it's like the duck walking across and you got to shoot it with a ball or a BB gun or something, and you hit it and it goes patink, and then it goes the other way? Anyone ever seen the end credits scene in Super Troopers? It was like 2 people who were like, it's a great movie. It's horribly inappropriate for school. Don't watch it here. But seriously, watch it somewhere else. Super Troopers. Oh, it's good. It's so wrong, but it's so good. Anyway. Every time you hit that negative, it is a change in direction, a change in signs. So like here, think of it as it's got a negative, and then I'm going to put 1, 2, 3, 4 negatives on it. So it's going left, it changes direction, it changes direction, it changes direction, it changes direction. Going left, negative town. Okay? Some kids that helps them. Some kids are like, what the is this? Okay? All depends. Count your sign changes. 2 for the first one, 1 for the second. So that tells me that there is 2 or 0 down in pairs. Possible negative real 0s. There is 1 possible negative real 0. Another way that this can help me is if I'm doing that guess and check thing. Remember, as I'm doing the guess and check, if I ever run into alternating signs or all positive signs in my synthetic division, it tells me if it's an upper or lower boundary. So I'm able to narrow in as I'm guessing and checking. Well, Another way that this helps me is, what if I started with negative numbers first, and then I find it on the first go? I can ignore all the other negative numbers, right? Because there's only one negative real zero even possible. So if you find it, well, it was in the last place I looked. Go to the positive ones. Okay? So like for 5a, I would start with the positives. Once I find that positive, I would quit and move to the negatives. It just helps you narrow down your options. Now, we're going to be working smarter, not harder. I still got to show you Descartes. But after that, all right, we need some practice. Finding the zeros. I know this is one of those like check pages. I'm just going to use them as extra problems. This guy. Find all the zeros. We got options, don't we? That's what we're practicing. Okay. If I say find all the zeros of this. Now there's Descartes' theorem. There's the rational root theorem. There's the upper and lower boundary theorem. There's all these theorems that help us. But you know what? I think that I'm just going to like gaze into the crystal ball. I'm going to commune with the ether, and I'm just going to guess a zero really good. I'm going to say x to the third minus x squared minus 8x plus 12. Graph of a. Now it's all factors of 12 over 1 that are possible rational zeros. But I tell you what, I'm feeling really lucky about trying 3. Or sorry, negative 3. Just got a feeling, right? So we'll go to synthetic division. 1, negative 8, 12. And say, you know, I'm going to try negative 3. For some reason, I got a feeling about negative 3. I get negative 3 here, negative 4, 12, 4, negative 12. Dude, I'm so good at this. And I look at that and say, you know what? I got a feeling about 2. Just, I don't know what it is. Something about 2. It just makes me think this might work. Dude, I'm so good at this. And then, for some reason, I think that 2 might work again. And notice at the end, I get 1. I get that 1 at the end because that means there's no GCF pulled out of any of these factors. This is also how you can reverse engineer the factors of a polynomial. I know that x plus 3 and x minus 2, the quantity squared, makes this thing. Okay? Do I want to show you that? There is a method of factoring this. It involves adding and subtracting in the same term. I haven't seen any textbook adequately explain this. I'm going to leave that for now. Okay. I might show it on 1 or 2 problems when it's really simple, but for now, not so much. 2, I could do that same thing, right? I could just plug it into my calculator and I could feel really, really lucky about plus or minus 1, plus or minus 3, plus or minus 1/2, plus or minus 3/2. Or, do y'all remember factoring by grouping? Do you see it? Do you see the 2x minus 3 on these? Factoring by grouping says I can cut this in half right now. What do these two got in common? X squared, leaving 2x minus 3. Well, those two got in common. Okay, they're relatively prime. They really got nothing. So I would normally put a 1 as a placeholder, but if I do, I have a negative 2x plus 3. I don't want negative 2x plus 3, so I'll take out a negative 1. In which case, I now see they both have a 2x minus 3 in common. So if I take that out, from both terms, I see there's a x squared minus 1 left over. I ain't done yet because this is the difference of squares. Difference of squares says square root of a, square root of b, plus minus conjugate pairs. Yes, ma'am. All right, good talk. So I'm going to go 2x minus 3 with x plus 1 and x minus 1. Set each equal to 0 and solve. X is 3/2 plus minus 1. Okay? Test, right? We got someone who's got a... What is... Today's a white day, right?
Yeah.
Oh, sweet. Quiz 4. If I do, it's in that bin back there. Okay, and I just care that you review so you're not going in blind. But you can absolutely just do it in a notebook or something. Are you okay doing it in here and just headphone jamming, or okay? Have you come over here? I always got those tables full or ready. But if that's too loud, Jameson has prep right now, and he'd be cool if you just going down there. All right. So I bring up that because these polynomials are about to get bigger and uglier. This is in quadratic form, and it's in quadratic form of a perfect square trinomial. Do you remember how to factor it? It's in the form of a perfect square trinomial right now. Oh, no, it's not absolutely perfect. Okay, it's not an item squared, but you can still factor it like quadratic. Y'all, it's set up like quadratic form, right? We recognize that part. Isn't the only way you're going to get 1 at the end with 1s? So I can factor just by putting a 1 here and 1 here. I know that's going to happen. Now you test the different factors of 36 in your head, or go full AC method on it. But it's going to be double negatives. That's the only way I end up with a negative term in the middle. With a 9x squared and a 4x squared. 6 and 6 makes 12, not 13. Okay? If you can do that by mental mojo, have at it. If you can't, y'all remember AC method, right? 36 times 1. What factors of 36 add up to negative 13? So I'll break that into 36x to the fourth minus 9x squared minus 9x to the fourth plus 1, or sorry, not 4. And then I would take out here a 9x squared, leaving 4x minus 1. Over here, negative 1, leaving 4x squared minus 1. Taking out a 4x squared minus 1, leaving a 9x squared minus 1. Like, you can do full AC method. I'm telling you, you've been doing quadratics for like 2-3 years. I trust you to get from here to here. Box method, the cross thing, like whoever you had it. There's different ways, right? But once I'm here, can you keep going? Because these are both difference of squares. Square root of A term, square root of B term, plus minus conjugate pairs. So this is going to get me 3x plus 1, 3x minus 1. 4x plus 1, 2x plus 1, 2x minus 1. Okay? Which means my zeros are at plus or minus 1/3, plus or minus 1/2. Maddie, I hear you talking trash about one of my students like that again. We're going to throw down. Okay. But do you see how close all of these are if I were to graph it? I want you to graph this. Like literally, just put this into y1 and look at the graph. Look at how squished together it is. Yes, very squishy. Think about that. The zeros are plus or minus 1/3 and 1/2. Very squishy. Right? You get a big W like this, where all of those zeros are in the interval from -1 to 1. So would that have been kind of difficult to do by synthetic division and guess the right number? Maybe. Depends how good your eyeballs are, right? So what I'm saying here is that there are different methods. You can gaze into the crystal ball and just guess really, really well with synthetic division. Ponder your orb, if you will. Or there is factoring. Have you ever factored a quartic like that? 5 terms. It is factorable. So yep, we're on to the next one. So let's start with, so we actually know what the answer is. Dump that into your calculator. 2, 9, negative 87, negative 49, 45. And say, I feel really lucky about what? A -1? All right. Holly feels really good about -1, so I'm just going to start there. -2, 7, -7, -94, right? 94, it's 45, -45. Okay, so that worked. Yay. How many real zeros did you just see? So what are the other ones?
No, I see 4.
You do see 4?
There is 4.
It's -9, -1, 1/2.
Ooh, okay, cool.
There's a lot.
Because it doesn't always work that way. Okay, what was something else? I heard a -9.
-5.
-9 to -18, -11, 99 problems. Math ain't one. Negative. Whoa, 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 whoa. Okay, I just took out 2 factors, 2 zeros. What do I got now? 2, -11, 5. What kind of polynomial is that going to create? Quadratic. Okay. I could factor that, or do I feel lucky about other numbers? A half? Okay. 2, 1, -10, -5. Careful. Before I proceed to the next line, divide by 2. Call this 5. No, not 5. 1. Well, you know what? I'll leave it there and I'll show you why this is necessary. If you stick 5 here, 2, 10, but look at what's left at the very end. So what we have here as a factored form is x plus 1, x plus 9. Because I wrote it like this, x minus 1/2. Right? X minus 5. And because there was that 2 left over at the end, I know there's a 2 out front. Yeah. This is the fully factored form. Same difference. They're the same polynomial. I'm just saying if you want the factored form, you better remember that 2 is there. Or divide by 2 right here and then keep going. In which case you would call this one 2x minus 1 instead. It seems like semantics, but if you do or do not have that 2, what you're doing is changing kind of the amplitude of your polynomial. If I don't have that 2, then I'm going to have something like 9, what was it? -9, -1, 1/2, 5. Versus if the 2 is there, I'm going to have -9, -1, 1/2, 5. They're going to have the same zeros, but they are not the same polynomial. Because one, think about transformations, is vertically stretched twice as far as the other one. They're not going to have the same extrema.
So which one's the correct one?
Well, you're going to get the same zeros. I'm saying it's not the same function. You can have two functions with the same zeros, right?
Yeah.
It seems like a small thing, but we're about to also find full factored form. We're about to do linear factorization. We're about to construct the polynomial, and that will matter. Okay, it's a small thing, but it is something to keep in mind. Factoring. We've seen quadratic form a few times now. Does anyone see a quadratic form in here? What if I took those three terms, set them over here, and then these two terms, and set them over here? Because now this one, 2 times 45 is 90, factors of 90 that add up to negative 87. I can turn this into a pair of binomials with x squared. I can take out a GCF here. And then what's going to happen is this and this are going to be the same. Factor those out, getting a perfect square, or a sum or difference of squares here, and then a quadratic that you can factor. Okay, so that's getting into the next level. I know we got a bunch of stuff written here, so I won't do it. Instead, I'm just going to say, however you do it, factor or synthetic division, solve. However you do it. We're doing this now where they're all, I believe they're all real zeros, because we're about to do fundamental theorem of algebra that says some of them are imaginary. Okay, so we're just kind of practicing the different methods right now, so we're good for the real game. Mm. No, it's not. It's the operator.
Operator error.
Okay, maybe it is a calculator. What did you do to it?
I didn't do
Yeah,
anything.
Jacob, what'd you do?
I just went to turn it on and it started blinking.
Okay.
It went blinky blinky.
Never with pencil, always with pen. Okay, now when we restart it, see how it's dimmer? Make it brighter. Good to go. Okay. We owe Jacob an apology. It was the calculator. If you tried factoring this, stuff's going to get raw on you. Okay, it's not really going to work out for us. There is a way. It involves splitting that negative 17x somehow. And this is why I'm not really a fan of making kids do this method, because I've never seen a textbook that can explain how I'm supposed to split that 17. It's just kind of guess and check numbers in your head. So, step one, everyone to one side of the bus. Okay. Now I'm guessing most of us dumped it into our calculator. We did our synthetic division. We got there. I have kids who will go past pre-calc. They'll go into calc. They'll be doing like calc 1 or 2, dual credit, something like that. And they come back to me and they're like, wait, how do I do this? Because I didn't stress this type of factoring enough. There is a method when I can break this into 4x minus 21x. You see how 4 minus 21 is still negative 17. Okay? I've never seen a textbook say why it's specifically those numbers, beyond just guessing and checking. And I hate that. But if you can guess and check your way into those two numbers, now watch over here. Take out an x. X squared minus 5x plus 4. Over here, take out negative 21. X minus 1. Take a look at that quadratic. That's factorable. It turns into a x minus 1, x minus 4. Now do you start to see how the pieces are going to come out? There's a pair of x minus 1s. This x minus 1 and this x minus 1 come out. But you have to be careful about what is now left. If this goes away and this goes away, this is an x with still an x minus 4. So over here we have a x squared minus 4x minus 21. And then that one is factorable. X minus 1, x minus 7, x plus 3. X is negative 3, 1, 7. Which I'm sure you saw on your calculator screen, which I'm sure you were able to do synthetic division with. But this, I have never seen a textbook adequately describe how you do that besides just guess and check. It does suck. But there is a way to factor these if it's not immediately factorable by grouping, and it involves splitting terms like this. And that's tough. I'm not going to lie, that is tough. If I'm at that 6 hours or less of sleep mark, I'm going to stare at that number for about 10 minutes and say, screw it. I'm going to go get my calculator. Okay? I'm just letting you know this is a thing that exists. All right. This one is easily, quickly factorable by grouping, right?
Yep.
Hold on. 7, 5, negative 4, negative 3, 5. Nope, that's a split one again. All right. You cool finding the stages with synthetic division all the way down?
Yeah.
Okay.
Oh, yeah.
Fundamental theorem of algebra, mentioned it a couple of times. It says if I got a degree n polynomial, I got n zeros. They might be rational, they might be irrational. They might be real, they might be imaginary. But there's n of them. So I can find them all. Okay, a polynomial function with degree n, the degree has to be greater than 0, because you can't have x to the negative first, because now it's not a polynomial. Has at least one 0, real or imaginary, in the complex number system, meaning if it's got n zeros, it's got n complex numbers. Complex numbers, if you remember, have a real part plus an imaginary part. A plus bi. Real part, imaginary part. We did this all the way back, chapter 0, section 2. And if I have a plus bi, because the only way I get I is by square root of negative 1, that means there also exists a minus bi. If a plus bi is one of them, a minus bi is one of them. They always occur in conjugates. That also works for radicals. Like if I had 3 plus square root of 5, that implies that 3 minus square root of 5 is also one of my roots. If 6 minus I is one of my roots, that implies 6 plus I has to be one of my roots. That is the conjugate root theorem. You have to get conjugate pairs, or else that was impossible. Said I unlocks a lot of stuff in math. So, write a polynomial. Y'all probably remember this from algebra 2. Write a polynomial that has these zeros. So, if negative 2 is one of my zeros, what's the factor that made it? Okay, you don't have to write this line. You don't have to write this line. It's a little bit overkill. But technically it's x minus negative 2. Technically it's x minus negative 4. Technically it's x minus 3 minus I. Right? Whatever the 0 is, x minus that is the linear factor that made it. Ah, crap. Okay, and if 3 minus I is one of my zeros, got him. What else is? So that means x minus 3 plus I is one of my factors. Now, I'm not going to write this entire line out because we know to just write this as x plus 2, x minus 4, right? Now, I have to ask, because everyone's coming in here from different Algebra 2 experiences, did your Algebra 2 teacher show you the cheater for conjugate zeros? It's a formula, like this is the quadratic that made it. Or did they make you distribute this out every time? Okay. Most Algebra 2 teachers will show kids this, but this formula is in no textbook ever. I have never seen this in a textbook. I've taught out of 9 different Algebra 2 curricula. I've never seen it in a textbook. Okay, all right, we'll get there. So, we'll get there. So this is x minus, we said 3 minus I, and x minus 3 plus I. Now, it's going to be really hard to distribute with something that has parentheses in it anyway, right?
Yeah.
So the first thing that I'm going to do is take care of these so that I don't have parentheses inside of parentheses. I'll call this x minus 3 plus I, x minus 3 minus I. Be very, very careful when we're talking about conjugate pairs. A lot of kids have a tendency to try to do minus 3 plus 3 here. This is why I'm writing out what the actual linear factor is. It's minus the 0. Over here, if I were to disturb it, I'll get x squared minus 4x plus 2x minus 8. Combine like terms. Hold on, 5. So that's going to be green, so that's going to be yellow, so we'll do yellow. X squared minus 2x minus 8. Okay, that other stuff, you should remember doing this. This is like a big core part of the polynomial unit in Algebra 2. You got to go distribution bonkers on it, and this is when I said, you multiply these however you multiply. Some of us would like to stack them together like old school 3-digit multiplication. Some of us are going to leave it like this and draw all those arrows and spaghetti monster the crap out of it. Some of us are going to like box method for these because your like terms are always going to be on the diagonals. Yeah, you can.
At the same time.
X negative 3 I, x negative 3 minus I. Right? Instead of Punnett square, it's like Punnett cube. Okay? You can do that. Absolutely. So you multiply them however you're going to multiply them. My personal preference is I distribute, but I keep them stacked so that the like terms are always lined up. If I take x times this stuff, I get x squared minus 3x minus ix. Right? X times the other stuff. All I did was distribute. Cool?
Yes.
Now I'll take negative 3 times the stuff. Negative 3 times x is negative 3x, so I'll write it here because they're like terms. Negative 3 times negative 3 is 9. That is not a like term with any of these. I'll write it over here. Negative 3 with negative I is plus 3i. I'll write it out here because it's not a like term with any of them. I'll distribute I to those. I times x is positive ix. I'll write it in this column because it's a like term with the other one. I times negative 3 is negative 3i. I'll write it out here because it's a like term with that one. I times negative I is negative I squared. I'll write it out here. There's no other like terms with it. All I did was organize my distribution. You distribute however you're going to, but then you do have to combine like terms. I find that this helps me organize my stuff. Box method is also great for this. But look at what you get at the end. I get an x squared here. I get 2 of these terms, negative 6x, and these 2 are always going to cancel out. These 2 are always going to cancel out because of the conjugate system. What is I squared? So this is really plus 1. 9 plus 1 are now like terms. I'm going to put plus 10 right here. We all got to get to this spot. You got to go again because we ain't there yet. This thing has 4 zeros. I need a quartic by the end of the problem, but I have a quadratic times a quadratic. Again, box method, stack multiplication, spaghetti monster, whatever your jam is. If I take x squared times that stuff, I'm going to get x to the fourth minus 6x to the third plus 10x squared. If I take negative 2 times the stuff, or negative 2x, get negative 2x cubed plus 12x squared minus 20x. If I take negative 8 times that stuff, negative 8x squared plus 48x minus 80. And I combine like terms. By the end of the problem, we should have f of x is x to the fourth minus 8x to the third. I see 22 minus 8, 16, right? 14. Yeah. 14x squared plus 28x minus 80. Write a polynomial function of least degree that has these zeros. I'm going to write x minus each of the zeros and then go distribution bonkers on it. Yes, ma'am. Oh. This should have been a negative 8. Negative 2 by, or 2 by negative 4 is negative 8.
Okay.
Yep. There's a lot of moving parts here. I think the one time that I actually counted, it was something like 48 different pieces of arithmetic. There's a lot of places to go wrong. Okay. I got to know where we have space. What about the previous page? Do we got some space anywhere there? Previous page, 7.5, not really? Okay. Wherever you got space to do one set of 3-term multiplication, I'm going to show you why there is a cheater. We said that a plus bi, if that's a 0, what else is a 0? Wherever you got room, wherever you want. A minus bi. Okay, that's what the conjugate root theorem says. I am going to do the multiplication of these as zeros with no numbers there. Just like when you did complete the square on a quadratic to find quadratic formula. So we got x minus a plus bi is one of my factors. We've got x minus a minus bi is one of my factors. Can you distribute that? It's just alphabet soup. Can you distribute that? Try. If you do, you should get the cheater. You should get the quadratic form that creates every single complex zero. Distribute it out. See where you get. This is some pretty abstract stuff. We took away all the numbers. Okay, if the top of your head is starting to feel warm, don't feel bad. And what, just for our box method fans. Let's go. 8. A. Here, I'm just going to kind of put these in columns here so you see what I'm doing as I line things up. Okay, all I was doing was lining up like terms as I went. Okay. And box method, again, works really, really good for keeping this organized. Most kids who like box method are probably ones who would have loved flow proofs in geometry. But I know that both of our geometry teachers hate flow proofs, so they don't show it too much. Depends who the hypervisual ones are. We were talking about this the other week as a math department. Spear enjoys paragraph proof. It's his favorite method. Right?
Well, it includes the word proof in it.
Okay. Are we getting the distribution of it? Now, look at what happens at the end of this, even with no numbers there. I'm going to have 2 of these terms. These terms are going to cancel out. These terms are going to cancel out. And I squared is -1. So I get plus a squared plus b squared. Now, if you got that cheater, watch how much faster this goes. This is my A. There's a 1 in front of here. That's my B. X squared minus 2A x plus A squared plus B squared. Now this is x squared minus 2x minus 8. Now this is x squared minus 6x. 9 plus 1 is 10. Then multiply those two.
That's so much easier. Does that work for everything?
Every single complex number.
Yes.
But we just did the proof for A plus BI. I can make A and B whatever the crap I want. And then after this, you see how just you keep going, right? I'll show you. This also works for conjugates that don't have I. Say it was a plus square root of b. There's no i's there now.
No, I-
That's okay.
But if square root of b was there, what else is there? Negative. A minus root of b. So that means x minus a plus square root of b. I swear that's a b. X minus a minus root of b. And I do the exact same thing here. And watch what happens at the end of it. X by all the stuff. X squared minus ax minus x root of b. Negative a times the stuff. Negative ax plus a squared minus a root of b. Negative root of b times the stuff. Negative x root of b. I should have wrote that the other way. Plus a root of b minus b. Or technically, root of b squared. See the same stuff? This term cancels out, this term cancels out. I still have x squared minus 2ax. I'm still going to have a squared, but now there isn't an I squared at the end to change my signs. So we'll do plus a squared minus. Now I'm going to switch this to saying b squared in such a way that whatever this term is, if I just say a plus b, where b is a radical. The exact same cheater works if I just change a sign when there's not an I. So now imagine I give you something like 5 minus 2 root of 3 is one of my zeros. Do you want to do this? Right? Because that's true. Do you want to do that or cheater town? X squared minus 2ax plus a squared minus b squared. And you just look at your a and b terms. A, b. And technically it's a negative, but you're squared, it's going to go away. Look at how much faster that algorithm is. 5 squared is 25. 2 root of 3 by 2 root of 3 is 12. Plus 13. Never seen it in a textbook.
That's the mic drop.
Never seen it in a textbook. Even in all of those Algebra 2 books that we looked through for the last couple of years. Never seen these formulas in an Algebra 2 textbook. But most Algebra 2 teachers show their kids this because, God, is that faster.
They've been cheating.
Okay? So, what I want you writing, this is nowhere in your notes, this is nowhere in a textbook. You will not find this, if you would please. If you have a plus bi as a 0, x squared minus 2ax plus a squared plus b squared. That is the quadratic that made it. If you have a plus b, and I'm just going to aim at this and say b is a radical. Remember, that could be square root of 5. That could be 16 square root of 7 over 3. Whatever it is, it's a big honking radical term. The only difference is I won't have the I squared at the end to change this sign. So it's minus b squared. Please write these down. Dear God, they save us so much time. They save us so much time.
If there's a coefficient in front of the second one, do you just put that in?
I'm saying this entire term is a radical. So say for example, I had 1 minus 2 root of 3 over 5. I put this whole thing in for b. That's the radical term. Okay?
So if there's a radical anywhere.
Now, if it has an I, that supersedes, right? Never seen them anywhere. But most Algebra 2 teachers will start talking and they'll kind of point at each other Spider-Man meme style. Be like, dude, did you get this too? This is a thing. Why aren't they saying the thing? I don't know. So, we'll start with baby steps. When they say 1 multiplicity 2, you understand that that's x minus 1 and another x minus 1. If I got 4i, what else do I got? Negative 4i. So how many total zeros are there? 5. So what am I going to get at the end of this problem? A quintic, 6 terms. Because it's x to the 5, 4, 3, 2, 1 constant. All right. Distribution. Go disturb it. It's a lot of stuff, y'all. There's so many numbers flying all over the place. You have to be organized in how you work. Yes, sir?
So it's x minus 2.
No, dude. This is just a regular negative 3. It's not one of my special terms.
All right.
Just write x plus 3. The cheaters only use the cheaters when you have a complex number. If I just see negative 3, just write x plus 3.
Can't really use it here because there's no a.
Oh, you can. We talked about complex numbers. How can I turn that into a real and imaginary part?
0.
0. Your a would just be 0.
Since there's 2 of them, you just put
Yes, multiplicity 2 means x minus 1, x minus 1. Yes, sir? Okay. It's a lot of getting dirty down in the trenches. This is...
Is this just for one of them? So I have to, like, what's going on here?
Who what?
I don't know.
Okay, so you wrote out your cheaters. Cool. What are we doing over here?
And that's just for those.
Okay, we have x plus 3, x minus 1. I need an... Where'd you get 2 from? No, it's 1 happened twice.
It's so ridiculous. So just do. Get rid of this.
Yes, and replace it with another x minus
So
1.
it's just 2x minus 1?
Yep.
Oh, okay.
I said this is the official notation. We were using that cheater like chemistry subscript.
But for this part, like, do you have to write this, like, thing twice?
No.
For each one?
No. Because they're conjugates, this is going to happen.
Oh, okay. So then you just, like, would you use plus
I
or
would pick,
minus?
since, where'd my 0 go? Here, do this, and then do this. So since this can be written as 0 plus for I, 0 is my A, 4 is my B.
Okay. Should I do it?
Okay?
So you plug 4 in for the B.
Mm-hmm.
And
0 for the A.
0 for the A. So those two are non-existent.
Correct.
So then it's just x squared plus 16.
Yeah.
So then you factor that. Yeah.
So you just have to choose in what order do you want to distribute that? 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Yeah. So we should have x plus 3, x minus 1, multiplicity of 2, it happened twice. And then you can either do the cheater, x squared minus 2ax plus a squared plus b squared, plugging in, get back here, a 0 and a 4, because I need to turn 4i into a complex number by doing 0 plus 4i. Or, you could just, because it isn't written as a complex number, you could just do x minus 4i, x plus 4i. They're both going to make x squared plus 16. Okay, both of them make x squared plus 16. Now, please be careful when you're distributing these that if I had 2 times 3 times 4 times 5 times 6, you don't multiply the 2 by all of them, right? That's silly goose town. So do not try to do x plus 3 times this guy and that guy. Okay? You choose how you multiply it, just like over here, you would choose how you multiply that. I'd pick numbers that are easier for me. I'd say 2 and 5 is 10. Times 3 times, I would do, I don't know, 24. So that's 72 by 10, so that's 720. I would choose in what order I want to multiply them. Just like here, I'm going to decide, personally, I think it's easier to multiply together binomials than trinomials. So that's how I'm going to multiply mine. If I distribute this, I get x cubed plus 3x squared plus 16x plus 48 with a x squared minus 2x plus 1. Okay, I just decided to multiply mine in that order because it made more sense for me. Doesn't mean you have to. When you distribute, find some way to organize it. I do mine in kind of that, it's like the spaghetti monster without the arrows, but I keep all of my like terms lined up in stacks. X squared by the stuff. So x to the 5th, 3x to the 4th, 16x to the 3rd, 48x squared. Go down to the next line, -2 by the stuff. -2x to the 4th minus 6x squared. Nope, 3rd. Where are we at? -32x squared minus 96x, then 1 by the stuff, x cubed, 3x squared, 16x plus 48. End of the line. Let's compare notes. X to the 5th plus x to the 4th plus 11x cubed. What's that? 1619 x squared minus 80x plus 48. How'd we do? What? 96 plus 16 is 80
Oh,
though.
it's 80.
How we both get 90?
I got 96 too. I got something
16
completely
times
different
negative
though, so I
5.
really screwed it up somewhere.
Wait. No, yeah, you're right.
Wait, what's the number I said?
I think we should be done for the day.
That's right. I got like 5.5 hours sleep. Get wrecked. So. Yo, this is pretty intense. There's just a lot of stuff moving. It's not that the multiplication itself is difficult. It's just there's a lot of it.
I got like exactly half.
Ruh-roh, Raggy. I think I have an idea because I heard you say you had x squared plus 16. Did you miss your middle term back here?
I had 3x plus 2x squared plus 6x plus 6. Because I multiplied x plus 3 times x plus 1 times x plus 1.
Unfortunately, they are x minus 1, sir.
Makes a lot more sense now. Yeah.
There you go. Found it. But seriously, if I see that on a test, I'm still going through your work. You did x plus 1 and x plus 1. Is everything else correct? Did you do everything else correctly?
I think so.
One off, domino effect. How many of you looked at those tests and you saw one little asterisk with a domino next to it? Okay? I'm never going to punish you and say, well, this problem is worth 10 points and you were wrong from here onward, minus 9. No. I would say one off on that, absolutely. So, we're going to practice this more tomorrow. Your homework is only going to include ones like this with small bits of conjugates, but I want you to look at the next couple examples. Fractions and radicals and entire complex number systems. We are going to do that to start tomorrow. Uh-huh.
All over this year.
Wait, they're still going?
Yeah. I actually might stay.
Didn't original Scream came out when I was in like 8th grade.
I know. It's my favorite movie.
All right.
One of the best movies ever.
Yes.
I think I did it.